All right, here's example 1 of section 3.2, Riemann sums. So here's the problem. They want us to approximate this thing. What does that thing mean? Now, if you remember from our notes just previously, this is the area under this function from points 0 to 2. Okay, so we're in the intervals from 0 to 2. We want the area under that curve. Now, if we just sketch this curve real quick, 5 minus x squared, I know is a parabola with a y-intercept of 5. So I guess you can go, let's see. Well, I know 1 over, it should look something like this. Okay, I'm not exactly sure the shape, but there we go. Some downward parabola. Okay, this sketch is more for me to help me think about the problem, not necessarily to have extreme accuracy. But let's continue. We want to divide the interval into n equals 5 subintervals of equal length. They want us to use the left Riemann sum, include a sketch. Okay, so we're going from 0 to 2, and we need 5 intervals. Okay, let me just see. 5 intervals. 1, 2, 3, 4, 5. That works out pretty well. And hey, it's already broken up into parts very easy. I don't know why I gave nice numbers like that for you to just know right away that the width is going to be 0.4. But why don't we actually calculate it using what we just learned above. We know that the width, or delta x, is going to equal the distance between the intervals over the sub number of intervals, or we can say b minus a over n. And we know it's going to be 2 minus 0 over 5, which is 2/5, or 0.4. So we know that each rectangle is going to be 0.4. That's pretty convenient that this graph is already given to us that way. Oops. Okay, so let's figure out what a left Riemann sum looks like. To remind ourselves, I have this box right up here to help us remember what left, right, and mid means. So how this works is to know if it's a left, right, or midpoint Riemann sum, we say the height is located at the left part within each subrectangle, okay? Or the right part, or the midpoint. It just depends on what it's asking. In this case, we're looking at the left, so it means the height of each rectangle is located at the left part. Okay, so here's our rectangle. So the height, how high does it go? Okay, does it go that high? Does it go this high? I don't know. So the height of each rectangle is at the left part of each rectangle. Okay, so here's the left. Let me erase these. Okay, so here's my left side of the rectangle, and where it crosses the function, that is my height right there. Okay, and then you go straight across. For my next rectangle here, I look at the left side of my rectangle and find that this is the height right there, and then here, and then here, and then here. Now remember, these are rough sketches, so I don't know how accurate these are. So I don't want to eyeball a function that I just kind of sketched, okay? So instead, I have a graphing calculator here where I plugged in my function, 5 minus x squared. And if you plug it in your table, plug in numbers, oh hey, I've already done it, so that's nice. So there are the heights between 0 and 2, all 0.4 distance apart. So let's calculate what this is going to be. So we have rectangle 1, 2, 3, 4, and 5. So we know each of these have a width of 0.4, all of them. So I can say the total area is going to be 0.4 times all the heights. Now let's figure out what the heights are. So we know for the first rectangle, this is the height. And what's the x value of that for this function? We know the x equals 0 for that one right here. So x is equals 0. So this height is the f, is the f of 0 right there. So our first rectangle is f of 0 plus. Then what's the height right here? We know that that has x value 0.4, so that's the f of 0.4. The f of 0.8 plus this height right there is the f of 1.2. And then to continue, we got plus for our final fifth rectangle. This height, you can find the location is here for this parabola at 1.6, f of 1.6. And you can use the graphing calculator to do 0.4 times f of 0 is 5 plus 4.84 plus 4.36 plus 3.56 plus 2.44. And you will get an answer of 8.08.